Another really important factor to consider when we're talking about how circuits behave in our grid is the surge factor. The surge factor describes what happens in the instant that we close a switch on a circuit. On the left here, we've got a little fictitious circuit with a capacitor in it and a switch and a voltage source. And on the right is a little plot that shows what's happening to the current through that capacitor as a function of time. Let's have a look at that capacitor in closer detail. A capacitor can be modeled by a simple set of parallel plates separated by some space. At rest, there are some population of electrons that exist on both of those two plates. But the moment we close our switch, we inject current into the top plate and current will be pushed out of the bottom plate. Eventually though, that top plate fills up with electrons and there's no more space for those charge carriers to occupy, and that bottom plate is almost devoid of charge. This is the point at which our capacitor is fully charged and we've reached steady state. This relationship can be described by a mathematical equation that says for a perfect capacitor, the current flowing through it is proportional to the quantity we call the capacitance, which we can think of as being simply proportional to the size of the plates in this simple example, multiplied by the rate at which the voltage across the capacitor changes with respect to time. If our switch closes instantaneously, meaning the rate at which the voltage changes across the capacitor is infinite, then we would expect an infinite current, which might look something like this. In the real world though, switches don't close instantaneously, they close slowly, and so there may be some start point where the switch begins to close and an end point at which the switch is fully closed. If we assume the voltage across the capacitor linearly ramps between those 2 points, then the current flowing through a capacitor is given by this rectangular function shown in blue. In practice, of course, there are parasitic resistances, parasitic inductances, and non-idealities associated with both our capacitor and our switch, and so a more realistic example of what the current looks like when we turn our circuit on is shown here in blue. We can see a big spike some time after the switch begins to close before we eventually return to steady state. This spike in current is what we call the surge current, and the ratio of this to our total load is our surge factor. So what other loads present a surge current? One of the more common loads in our household are magnetic circuits, and these include things like transformers and AC and DC motors. In this case, the inrush current occurs at the startup due to the energization of the magnetic core, or the magnetic circuit. Systems with materials exhibiting temperature-dependent resistance also present a surge current, for example lighting. And in the case of traditional incandescent bulbs, this occurs because the resistance through the filament at room temperature is different to the resistance through the filament once it's lit. And so that change in resistance happens over a short period of time, which leads to an inrush current. Similarly, resistive coil heating presents a similar problem for much the same reasons. The resistance of the coil changes as a function of the coil's temperature, and so we have a current that changes with respect to time.